Hi, this is Dave Johnson with another edition of Math Off Topics. And today, if you're watching this video, maybe it's because you're taking your calculus course for the first time or thinking about taking calculus. And I couldn't be more excited for you. When I was in your shoes way back when, uh, the idea of taking calculus was very exciting to me. I think of calculus as like the launch pad for the rocket that's going to take you into upper mathematics and engineering and physics. Without calculus, you wouldn't be able to do those things. And so I wanted to share some insights, and one of them is calculus. If you understand one idea, so I'm going to give you the one idea that you need to understand. Um, if you do that, you will probably do pretty well in calculus, and that's understanding the derivative. You may have heard things about the derivative. If you don't know anything about the derivative yet, don't worry. They're going to teach it to you. The first 3 or 4 weeks of a calculus course might be review, might talk about limits, but until you get into the derivative, you're not really doing calculus yet. At least that's my humble opinion. Nothing wrong with all those other things, but the derivative is where it's at. In fact, I think of the derivative as the heart and soul of calculus. And so in this video, I wanted to give you a sneak peek at the derivative. So let's get into it. And I'm going to do this in a way, hopefully, that meshes very well with what you already know from algebra. So we're looking at a line, a straight line, and I've marked off some points here. Your x1, y1, and your x2, y2, and the you can kind of figure out where we're going with this. I'm going to find the slope of that line. So let's just go ahead and do that. So typically we call m the slope, and m is what? Y2 minus y1 over x2 minus x1. I want to mention that at this moment, I'm thinking of x1 and y1 and x2 and y2 being fixed. In other words, those are fixed points. And in a minute, we're going to make some adjustments. But that's what the slope is. Now, what's the big deal? I mean, you already understand this, right? It's the slope of a line. I mean, you've been doing this since high school algebra or college algebra. But I want to suggest the possibility that not every relationship, every mathematical function is a straight line. That in fact, the interesting functions don't tend to be straight lines; they tend to be curves. And so let's just introduce the curve here, and I'm going to call that f of x, and I've labeled that in red. And so we can still take that curve and identify 2 points, x1, y1, and x2, y2, that are on the curve and find the slope of the line between those two curves. This is known as the secant line, and that's just terminology, vocabulary, not really that important for what we're doing right now. But so I want to make some notational changes because what I want to do is I want to work my way from this simple idea to what we call the derivative. And so the first thing I'm going to do is recognize that the y1 is the same as f of x1. And that you know that from college algebra or high school algebra. It's just a typical function notation. The y2 is equal to f of x2. And so I'm going to go ahead and make that substitution in our equation here. So it's still the slope of the same secant line, but y2 is going to be replaced with f of x2, and y1 is going to be replaced with f of x1, and then still dividing by uh, x2 minus x1. Okay, Now we're going to introduce a little bit more notation. And uh, by the way, you may recognize this if you've had college algebra. This is the average rate of change. So let me just call this the average rate of change. So it's you may have already seen this applied to curves, but the idea is you pick 2 points on the curve, you find the slope of the line between the two curves, and we call that the average rate of change. And so I like to call it the AROC, okay, average rate of change. And notice the average rate of change is the slope of the secant line. So let's go a little further, introduce a little bit more notation here. So this difference between the x1 and the x2, I'm going to call that h. Now, why do we use h? Well, that's kind of a modern thing. Older textbooks don't call it h, but almost everybody nowadays does. And so what is h? Well, let me just over here say h is equal to x2 minus x1. But let me also, let's solve for x2. If I add x1 to both sides, we get x2 is equal to x1 plus h. Okay, nothing hard algebraically here. If you're following along, you haven't had any calculus yet, and yet, believe it or not, we are doing calculus. Okay, so let's go ahead and make these substitutions into our expression for the AROC, our average rate of change. And so this is going to, so the f of x2 gets replaced with f of x1 plus h. The f of x1 gets replaced with just plain old f of x. In other words, it doesn't change. So f of x1 there. And then our downstairs, let's go ahead and change that. The x2 minus x1, remember we defined that to be our h. So let me put an h downstairs. So for those of you who already know calculus, this is going to start to look a little bit familiar. And I won't give it away yet, but let's just keep going. The next thing I want to do is I want to relax the constraint that x1 and x2 are fixed points. And so in other words, what I want to do is I want to remove the subscript on the x1. So let's say get rid of subscript on x1. What is that going to do? Well, now we can think of the x1 as being variable instead of being a fixed point. I'm just going to call it x. And so let's make that change. So f of, well, the x1 becomes x plus h minus f of x, and then divide by h. Now we have, it's basically the same thing. Notice these are equal signs. M is equal to this, which 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 is equal to this, assuming that these changes in notation have been made. I want to do one last thing. I'm going to call this the difference quotient, the DQ. So this is difference quotient. In other words, it's a quotient of differences. The numerator is a difference between two y values. The denominator, h, is a difference of two x values. And so we have now seen that the average rate of change is the same as the difference quotient, and it's the same as the slope of our secant line, which we started with. Now, the sneak peek at the derivative. The derivative, and I'm gonna throw this out there. You're going to see this over and over in your calculus class. It's just more notation. They say the derivative of y with respect to x is equal to the limit as h goes to 0 of your difference quotient. Now, I'm not going to explain that now because that would be giving away the fun stuff that your calculus teacher is going to be sharing with you. But if you understand everything that I've drawn here, including the difference quotient, then you can see why you study limits and really what the derivative is in terms of a limit of a difference quotient. And I know that's a lot, but it's all based on the algebra that you already know. And so I hope that's been helpful. I hope you've enjoyed the video. If so, please like and subscribe, and I will see you